Hi everyone, and thanks for joining us today for the exida webinar. We will go ahead and get started. So today we're going to talk about architectural constraints. We'll talk about what they are, how it was determined for a device, and why it's important, along with looking at the IEC 61508 and 511 tables. So if you have any questions throughout the webinar, go ahead and put them in the questions tab of your panel. And at the end, I'll save some time and go through any questions that you may have. Also, there's going to be a recording of this webinar posted on both the exida YouTube channel and the exida website. And if you signed up for this webinar live, you will get emailed a PDF of the slides later this week. My name is Loren Stewart. I'm a CFSE here. I work at exida and I focus mainly on our mechanical customers. I not only do FMEDAs and help my customers get SIL approval for their products, I also do training. So I go and I teach our FSE 100 and some of our other courses. For those of you that are new to exida, I want to tell you a little bit about who we are first. I like to say no matter where you are or your customers or the manufacturers are, we have someone close by that can help you with functional safety. So whether that's functional safety and process safety or alarm management or cybersecurity, we have experts in the field close by to help you. exida is involved with really the complete supply chain of functional safety. Whether it's OEMs building the devices, through system designers, end users, and engineering contractors. No matter where you fall, as long as you're dealing with functional safety, we have consulting experts, tools, books, and services that we can offer you. As I just mentioned, we have engineering and consulting services in not only just process safety or functional safety, but also alarm management and cybersecurity. We also have tools to help with functional safety, cybersecurity, and alarm management. These tools were really designed to help save you time and money. And they do that because they really increase your efficiency and your productivity. So if you're trying to do SIL verification or SIL selection, if you're doing PHAs, LOPAs, proof test procedures, if you're creating SRS, if you're trying to do alarm rationalization or cyber risk assessment, we have tools that can help you along in all of your needs. We also have certification. So if you are buying certified products or you're creating products to be certified, we have certification for you, whether it's in process safety or IEC 61508 or 511. If you need tool qualification, cybersecurity, machine safety, or even personnel certification, if you want to prove that you are an expert in functional safety, we also have personnel certification program. So getting to why you're really here is today's webinar. We're going to be talking about architectural constraints. We're going to look at what factors go into SIL requirements with functional or with architectural constraints. The different things you need to consider when you are looking at architectural constraints, and we're going to look at the tables themselves. Where do architectural constraints come from? Well, they are one of the 3 design barriers when someone is designing a SIF. You need to create or safety function. You need to check off all 3 categories or jump over all 3 barriers or hurdles. And these are designed by IEC 61508 and IEC 61511. The three barriers are systematic capability, or if it's SIL blank capable, the PFD average, or PFH if you're in a high demand mode of operation, and finally architectural constraints. And we're really going to focus on that last barrier, or that last hurdle, architectural constraints, today. If you want more information on systematic capability or PFD average, we have webinars just on those topics themselves. So if you want more information, we also have blogs and white papers on them as well. So check out our website if you need more information on one of those categories. As I just talked about, this is a different visualization of the SIF verification requirements. Once again, you have that SIL, or systematic capability. You have that probability of failure, or the PFD average, and you have your architectural constraints. And one of the main misconceptions in SIF verification requirements and with the standards is you might just think that you can only look at systematic capability, or only look at probability of failure on demand, or only look at architectural constraints, and you would be in compliance with the standard. Well, that's not the case at all. The standard says it's not just a pick one of these and you chose that route and that's how you're going to go. No, you need to look at it as barriers or hurdle, and to finish the race, you need to overcome or jump each of these requirements. And if you're doing perfect in two of these requirements, but you're completely forgetting the third, you're not in compliance with the standard at all. So as much as PFD average gets played up, and SIL, or systematic capability, gets played up, architectural constraints sometimes gets pushed to the background. So I got some questions about it, and I wanted to put together a webinar. So why are there even architectural constraints? If there's PFD average and there's systematic capability, why not just worry about those two and forget about architectural constraints? Well, there's a couple different reasons. You're always going to have some people that think that either the systematic capability or the failure rates in the PFD average, some people say, well, some of those aren't good, so they have the architectural constraints as kind of a sanity check, if you will. If, once again, it can be a sanity check. If somebody uses very low failure rate data, you need to maintain the design rules of the tables that we're going to look at to really ensure safety. And some people argue that probabilistic concept is not sufficient to ensure safety, that there needs to be another set of rules in place. So what does this look like in real life? Why do you actually should you care? Well, if you're not familiar, this is a screenshot of our Excellentia tool, and it does SIL verifications. And if you're not familiar with it, if you're doing SIL verification, you probably should be. It really makes SIL verification quick and easy. It already has the database built in. You just simply pick down the already certified equipment in the drop-down boxes. You build your SIF, and it runs all of the calculations for you. It's awesome. Anyway, so I wanted to put together just a simple SIF to show what real life examples look like. So I picked a sensor group, I picked a logic solver, I picked a solenoid and actuator and valve, and made a final element group. And this is what I came up with. So there's a few things that I really want to point out here. So first of all, this SIF is achieving a SIL 2 rating. So as you can see in one of the boxes pointing out here, says the safety integrity level is actually a SIL 2. And this is showing there's no redundancy and no diagnostics. So you might think that you just put together the greatest SIF ever. You can put this in the field. You never have to touch it. You never have to do diagnostics, no proof testing. You're a 1 out of 1 system. There's no redundancy. This is great. You're going to save money. Well, before you get too excited, let's take a look at some things. Let's move over to the other box at the bottom. Looking at just our final elements, and our final element, our subsystem, I guess, our final element group, we have a solenoid, an actuator, and a valve. And it is saying for that group, you have a failure rate of 12.1 fits, and fits are failures in time. For those of you that might not be familiar with fits or that unit of measurement, it is a unit of measurement that's 10 to the negative 9. So this is a very, 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 very small number. And it's how often you can predict something to fail. It has its failure rate. And with that, you can convert it to years if you're not familiar with fits. 12.1 fits converts to 94 or over 9,400 years. And that's your mean time to fail. So this is saying your SIF, and even just the solenoid, actuator, and valve, this is expecting you not to have a failure in over 9,400 years. Well, with mission time and everything, that's not likely, but another way to look at this is you have 9,400 SIFs or 9,400 valves in your plant. This is saying only one of those will fail per year. And if you're used to being out in the field, you have a lot of SIFs you're looking over or a lot of final elements that you're looking over, you might, that number might raise your eyebrows or might make you a little surprised, and it should. Another thing to point out is in our pie graph here, there's a lot of red. And there's not very much blue. That blue color is showing your final elements. And your final element is really only taking up 5% of your PFD average total contribution. And if you're familiar with valve actuator solenoids, they're actually normally take up a majority of your probability of failure on demand. With your sensors, your logic solvers being smart devices, you usually have much lower failure rates, lower contribution to your PFD average. So, like I said, this kind of will raise an eyebrow. So this is what I would consider extremely optimistic data. These were, I got these numbers by entering my own failure rate data into into Excelentia, overriding what was normally there. And as I said, I would consider this extremely optimistic data. So I wanted to then show you what a realistic data would look like. This is, once again, our Excelentia tool, and everything stayed the same, except this time I put certified and verified failure rate data in. As you can see, now our pie graph, instead of being mostly red with some yellow, it's almost all blue. Your final elements are your main contributors to your probability of failure on demand calculation, which is more realistic. At the bottom, your final elements, your solenoid, actuator, and valve, instead of being 12.1 fits, it's over 1,300 fits. This is much more likely. So that then converts to a mean time before failing of 87 years. Once again, we're not saying that you can put a valve in operation for 87 years. It's more like think you have 87 valves in your plant. You might see one failure per year. Okay, this is a lot more realistic. Now let's look at your risk reduction factor. If you're familiar, before we had a risk reduction factor of 780. Now we have a risk reduction factor of 37. That's a major difference. But what does that do to your safety integrity level? It drops it down to a SIL 1. So, which is fine for a SIF if that's what you needed. If your calculations, if you did your load bus and HAZOPs, you've done all of the calculations, you've figured out you needed a SIL 1, this is a great SIF. You can always improve your SIL rating. You might improve it by implementing diagnostics, changing your proof test intervals, changing your mission time. So there's a lot of ways to help you achieve a SIL 2 if you need to. The major problem is if you've done all of your calculations saying you need a SIL 2, you expect that you did your SIL verification and you expect that your SIF is running at a SIL 2, when in reality it's only operating at a SIL 1. Sometimes that might not be too much of an issue, but what if there are what if one of the safeguards it was guarding against is possible loss of life? And when you are operating an order of magnitude below what you should be, it could potentially be unsafe. So that's why architectural constraints are important. Now let's look at what they are. Well, architectural constraints is really the sum of the number of the devices required for voting and the number required for hardware fault tolerance, or HFT if you might have heard. It's really redundancy. There are two ways that this can really be done by the standard. The original standard, IEC 61508, came out with safe failure fraction, and you might have heard of that before. It enables you to take credit for good engineering practices. You're doing the right things. And in the 2010 version of the standard, when the second edition came out, it introduced a second method of qualifying and meeting this third barrier. And that's 2H, and that's looking at data quality. So looking at both of these in a little more detail, as I said, route 1H is your safe failure fraction, and you can calculate that by, there's equations in the standard and there's tables in the standard, and that will give you a minimum redundancy or a minimum hardware fault tolerance, which will give you a SIL level for each element. The second method is route 2H, and like I said, that's a little newer than your safe failure fraction, and that is based on your data quality, how confident you are in your data. And this isn't just, oh yeah, we only got a few back, I'm sure it's fine. No, this is much more in depth than that, and we'll take a look at in detail what it takes to qualify. But 2H takes away the safe failure fraction calculation, but it still sets minimum hardware fault tolerance or minimum redundancy by following a set of rules. So diving into safe failure fraction, or route 1H, it's going to be the safe failures. For those of you that aren't familiar with failure rates are that lambda character, and your total failure rate can be broken up into safe and dangerous, detected and undetected. So you, at the numerator of the ratio, you're going to have your safe detected failure rates, your safe undetected failure rates, and your dangerous detected failure rates. So these are the failures that are either going to cause a spurious trip to the operation, a safe failure, or a safe shutdown, or it could be dangerous, but it's going to let you know that it's there. It's going to be a dangerous detected failure over the total failure rate, or the safe plus the dangerous detected, and now we're including the dangerous undetected failure rates. And those are the failures that you really need to call your attention to. Those dangerous failure rates that could just be laying there sleeping without you knowing that it's in a dangerous phase. So whenever your safety function needs to be called into operation, it cannot do its job. So your safe failure fraction is going to be those safe failures over the total failures. The safe failure fractions are then, once you have your safe failure fraction or your percentage, you can then use two different tables in the IEC 61508 standard. Those two different tables are separated by product types. So you can have two types of products, either type A or type B device. They have a section in the standard that explains exactly what it is. I like to say it's a little more simple than this. Type A are like simple mechanical devices, where type B is your smart devices, something with a microprocessor or like something complex ASIC. Those are type B. So they can detect failures on themselves, where a type A is a simple mechanical device, your valve, your actuators. This is what the IEC 61508 Route 1H table looks like for a simple mechanical device. So once again, this would be your final elements that we looked at earlier, the solenoid, valve, actuator type devices. They're not smart. So if you are following your safe failure fraction, you did your calculations, let's say that you came out to 75% safe failure fraction. If you did your research, you know that for this safety function, you need a SIL2 operation. You can then go in the standard, use this table, and say, okay, 75%, SIL2, hardware fault tolerance 0. So you don't need an extra set of equipment. And we'll get into exactly what hardware fault tolerance means later. But say you have that same safe failure fraction, but your safety function, instead of a SIL2, you realize it needed to be a SIL3. You're going to have a hardware fault tolerance of 1. So that means you need one extra set of equipment to do that same job. Now, if where in fact it wasn't a valve, but you had some sort of smart device, let's say you still have a safe failure fraction of 75%. This time, everything, if you notice, kind of bumped down and to the right a little bit. So now instead of a hardware fault tolerance of 0 at a SIL2, you now fall into a hardware fault tolerance of 1. And now if you still need that SIL3 device or that SIL3 SIF, you are now going to have a hardware fault tolerance of 2, or 2 spare set of equipment. But the good thing, normally type B devices have a higher safe failure fraction than type A. So normally you would fall in that 90 to 99 percentile. But this, you still need to do your safe failure fraction, and you still need to use this table, whether it's a type A or type B system. The second route is route 2H. Once again, it talks about your data quality. How confident are you in the quality of your failure data? And the standard doesn't just say, oh, you have to have a warm and fuzzy feeling. No, the standard says you have to have high confidence, over 90%. And that 90% is more than just, we only got a few back. It's more than just statistical analysis even. You need to have a high quality data collection system. Not only that, you also, if you're collecting data to make your 2H database, you need to take into consideration similar applications and in similar environments. Application meaning if you, all of the SIFs you're looking at are close on trip application and you're starting a open on trip application, that's could behave very differently. What if different environments? What if you are actually putting your SIF topside or subsea? You can't take that information from a cabinet mounted or a inside climate controlled application environment and think that this is an apples to apples comparison. So if you are collecting data to try and build a high confident data collection system and high confident data, you need to do apples to apples. So what does the standard say exactly? Well, this is just one blurb from the standard, but it directly says that 90%. It directly says you need to have a similar application and similar environment. It directly says that you need to have exercise expert judgment, that this has to be something that you are very familiar with to use Route 2H. So how do you get that 2H information? Well, you can either collect a lot of field failure data from several different applications and several different environments, so you make sure you're completely covered, and use all the published field failure data and analyze those results. And that's what we did here. So we put together this huge database for Route 2H, so then we could start certifying devices for Route 2H as well. When you look at in IEC 61508, the 2H table, this is directly from the standard. As you can see, it looks a little bit different from the two tables we just identified. There is no safe failure fraction anymore because there's no more safe failure fraction calculation. But if you were to line up all of the tables, you would notice this column looks very familiar. It looks a lot like that type B if you were in the 90 to 99 percentile. Same, everything's lining up. Well, okay, what about the type A? Well, it's kind of lining up in the 60 to 90 percentile. And if you use IEC 61511, if you are an end user and you're more comfortable with that standard, you might think, wow, this really looks familiar. Well, it should. It's the same table as the proven in use for field devices. Note that is 1 through 3. IEC 61511 says if you are looking for a SIF 4 application, look back to IEC 61508. So it basically says SIF 4, not necessarily, but the tables are identical besides that. So we've talked about hardware fault tolerance already, but what is it really? Well, hardware fault tolerance is your measure of safety redundancy, and it specifies the number of extra sets of protection equipment. So if you have hardware fault tolerance 0, that means no extra equipment is needed. So you can have a 1 out of 1 system. Hardware fault tolerance of 1 means there needs to be at least 1 extra set of equipment. So if you have, if you need 1 set of equipment, you have to have 2 there. If you need 2 sets of equipment, you have to have 3 there. And this notation is usually shown as the moon safety notation, where it's how many is needed and how many are there. So you might have heard of 1 out of 1 or 1 out of 2. So 1 out of 1, your hardware fault tolerance would be 0 because there's no extra set of equipment. Along with 1 out of 1D, those Ds stand for diagnostics. So that's not going to alter your hardware fault tolerance. If you move to 1 out of 2, then you have 2 possible sets of equipment. Only one of those needs to do its job to shut down the process or whatever its job is. So you have 1 extra set of equipment there. So you're going to have a hardware fault tolerance of 1. Now, if you have 2 out of 2, you have 2, you need all 2, so your hardware fault tolerance is 0. And this can go on, 2 out of 3, 2 out of 2D, 1 out of 2D, 1 out of 3. 1 out of 3, you're actually going to have a hardware fault tolerance of 2 because you only need 1 of those to work, but you have 3 there. There's 2 extra sets. So this is just the same table that we looked at before. This is for type B, 1H, because it has a safe failure fraction there. And so we can see if you have a safe failure fraction of, say, that 75%. SIL 1, hardware fault tolerance of 0, so it could be a 1 out of 1 or 1 out of 1D. You could have a 2 out of 2 or a 2 out of 2D. However, if you need a SIL 2 application, you have a hardware fault tolerance of 1. So you no longer have an option to do a 1 out of 1. You now have to graduate to a 1 out of 2 or a 2 out of 3. And if you need a SIL 3 at that 75%, you have a hardware fault tolerance of 2. So you are going to need to use a 1 out of 3. This is just, the table to the left is just an example. You can have that architecture table could go on and on. I've seen 7 out of 8. I've seen 2 out of 4. It just depends on how you want to set up your system, but it gives you an idea of different examples on how hardware fault tolerance can be calculated. So what does this look like in real life? Well, let's say for a sensor, you have a pressure transmitter. You have pressure transmitter 101A and pressure transmitter 101B. Well, if you have a 1 out of 2 architecture, if either of those trip, it will indicate a trip condition. So if either of those sensors notices that there is an issue, it can signal that there's a trip condition, there's an issue, we better take action. If we're talking about final elements, it would be a 1 out of 2 would be something in series. If you have process fluid going through your valve here, your process doesn't care if it's the right valve or if it's the left valve that closes to shut down. Just as long as one of them does the job, the process will be shut down and the issue will be resolved. Things look a little bit different for a 2 out of 2 architecture. Let's look at sensors. Let's say that you still have your two pressure transmitters, 101A and 101B. However, now both of the trip of your SIF can only happen if both transmitter indicate a trip condition. So if one of those transmitters says, oh, we have an issue, but the other one says no issue, your system won't trip. If we look at final elements here, as you notice, it's no longer in series. We are looking in parallel. This voting 2 out of 2, the process fluid, it doesn't matter. It can go through the top valve or it can go through the bottom valve. So if one of those valves, say the top valve, indicates there's an issue, it closes. The process fluid can still go through the bottom valve and the process can continue. So you no longer have that extra set of equipment to do the job. So as you can imagine, a 2 out of 2 compared to a 1 out of 2, it's going to be more reliable. You're not going to have as many safe trips, or it's going to be, you're no longer going to have as many safe trips as if only one of them has to trip. However, you're not going to have the safety built in either. So comparing the architectures, you have your PFD average compared to your spurious trip rate. So compared to a 1 out of 2, 1 out of 1, 2 out of 1, or 2 out of 2 with diagnostics, 2 out of 3, you can kind of see there's a give and take with availability and safety. So depending on what's important in your SIF, you have to balance this. If you cannot have a spurious trip, maybe instead of having a 1 out of 2, you have a 2 out of 2 or a 2 out of 3. If you are more concerned about safety, you cannot have an issue. Maybe have a 1 out of 2 or a 2 out of 2 application. So you have to balance your architecture with how the SIF needs to perform. So we looked at architectural constraints today, how you need to know your type A or type B. That will help guide you which tables to use in the Route 1H or 2H tables. And you now know how to figure out hardware fault tolerance from those tables. But if you remember, there's other things besides just architectural constraints when you are evaluating your SIF and doing your SIL verification. So all 3 of these just fit into that one bottom circle. So if you're doing SIF verification, don't forget about the other 2. Make sure you still are checking your SIL capability and your probability of failure. And like I said at the beginning, if you want more information on either of those categories, check our website. We have webinars, blogs, and white papers on just those categories alone. So now I'm going to go ahead and take a time and see if there's any questions. And if you think of questions later, please feel free to email me. I'll get to them as soon as I can. We're kind of busy here, but that's a good thing. For more information, always check our website. We have blogs always coming out, webinars, usually weekly. We have our textbooks, our white papers, so there's a lot of information. And a lot of that information is actually free on our website. If you want to look at old blogs or webinars, feel free to go on our website or our YouTube channel. And if you loved this training and you are so excited about functional safety, you need to know more information, we also have training. So look at our training schedule. We have everything from short mini trainings to full week trainings that you can actually take tests at the end to show your competency. So if you want more information on that, feel free. Okay, so we have two questions here. The first one is about if an assembly has a solenoid valve, an actuator, a valve, are we classifying the assembly as a channel or the component as a channel? So when you are doing safe failure fraction, you need to be looking at the safe failure fraction on all portions of your SIF. And that's the same for route 2H as well. If you have a valve, you can't say I choose route 1H and safe failure fraction for the valve, but the actuator I'm going to do 2H, and the solenoid I'm going to, it doesn't matter for the solenoid. Whatever you do, route 1H or route 2H, you're going to need to do for your entire SIF. And a question on route 2H and the certifications. If you're picking a certificate that states route 2H, how do you know if the environment is considered the same as your environment? That's a great question. And I would say if you ever have a question, ask. If I can only speak for exida certificates because I've only worked at exida. I don't know about our competitors, but I know with the exida certificate, all of the environments and applications that have been considered are listed on the FMETA report and the assessment report. They're also going to be listed in the device's safety manual. So if you have a valve that is considered appropriate for subsea use, it needs to say in the product's functional safety manual that that valve can be used for subsea applications. And it will say that in all of the ones that we do here at exida. So when you're looking at the FMETA, it's going to give you failure rates for any application or environment that is appropriate. And then that 2H certificate is issued for the device in all of the applications it listed is appropriate. We have a suggestion for a new webinar, so that is wonderful. Thank you for that. I appreciate that. And I think that that's something that we had a question asking if we could do common cause factors for SIF component failures. And I think that's a great idea. So keep a lookout. We can definitely put one together in the near future for that. So thank you very much for that, Karen. That's all the questions for right now. If you think of any, let us know. And thank you for joining us today. Have a great one.